Principal root, or just root, as I will say, is a number that looks like this. This first square root symbol with a p there is radical of power p. And the b on the inside is called the radicand, also called an argument. So the simplified answer of the pth radical of b will be the same sign as b. That's the important thing to know here. So if b is negative, if b on the inside here is negative, then the pth root of b is also negative. However, we do not allow negatives under even square roots, even powers, even square roots, fourth roots, sixth roots, things like that. This makes it a complex number, and we're going to look at these a little bit later, but for now, we're not going to allow that. Now, because the square root symbol, when p is 2, is used so frequently, we're just going to use it as the just the radical by itself with no power on it. That means the square root. Now, the radical operation can undo numerical exponent. They are called inverses. Think of multiplication and division, addition and subtraction. When working with expressions that involve radicals, we have different rules, kind of like the exponent rules that we had in the previous video. The product rule is the pth root of two things multiplying is the same thing as the pth root of the first times the pth root of the second. So you can break up a radical over multiplication. The nice thing about this is it allows us to reduce roots by finding like a pth power factor in there, if that makes sense. The way we do this is we ask what nth power factor is inside a number. So for instance, the square root of 18, I can reduce this thing by looking at, well, 18 is the same thing as, let me do it over here. 18 is the same thing as 6 times 3. It's also 9 times 2. It's also, of course, 1 times 18. And in these, I'm going to look at this second one because we're looking at a square root, in other words, a power of 2. And it just so happens that 9 is also the same thing as 3 squared. So we have a power of 2 on the radical, and we have a factor with a power of 2 on the inside. 9 is 3 squared. So what I can do is I can break up the square root of 18 into the square root of 9 times 2. Using the product rule, I can break it up into the square root of 9 times the square root of 2. 9 is the same thing as 3 squared. And the square root and a square cancel each other. They are inverses. So that's the same thing as 3 times root 2. And this is what's called simplified form. The reason why is because the innermost thing has as many factors taken out of it as possible. And there's a number of reasons why we want to do this. It may not seem easier to work with, but it's actually better to work with, as you'll see later on. Now, in the second case, we have fourth roots. What I can do instead of breaking this thing up first off, I go from two things multiplying to one thing multiplying. This can be helpful when you have different parts that don't factor out. So like 8 is 2 cubed, and that cannot simplify instead of a fourth root. However, if we combine these two radicands, then maybe we can simplify something further. So I want to combine these two things in one radical. 8, we get 8x to the 5th times 14x cubed. Okay. 8 times 14, let's go ahead and do that. It's going to give us a 112. X to the 5th times x cubed, like bases multiplying, so we get x to the 8. Now, what we can do is we can break up the radical. 112 is the same thing as 16 times, 16 times 7. And 16 is 2 to the 4th power. And the 4th power is what I care about because I have a 4th root. Okay, and then x to the 8, well, that's the same thing as x to the 4th times x to the 4th. Again, the 4th power is what I care about since I have a 4th root. I'm going to rewrite 16 as 2 to the 4th power. And now you can see I'm going to break up the radical over each one of these things. Okay, and this simplifies down into 2 times the 4th root of 7 times x, or in other words, 2x squared times the 4th root of 7. And that is simplified form. So try out this idea of the product rule on problems in number 1. Okay, another rule that we have in radicals is the quotient rule. And very similarly to the product rule, if we have a radical over a fraction, we can split it up over the fraction, the top and the bottom. All right, now doing this for this first one, I've got 4x cubed, and hopefully you can see, well, x cubed and the cube root will cancel, and 27 just happens to be 3 cubed. On the top, I can use the product rule to split up the radical. And on bottom, the cube root of 3 cubed is just 3. Okay, now we have the cube root of 4 times x over 3. And that is simplified form. Okay, it may help to also combine the radical into one thing and then go from there. So in this case, I'm going to combine the radicals into one radical. And now I can cancel things on top and bottom. So first off, I can cancel 3 out of each. So we get 8. And then x, and this becomes x squared on top. We get 8x squared. 8 is the same thing as 4 times 2. This matters because 4 is 2 squared. So that square will cancel with the square root. So I'm going to get 4 times 2 times root 2. I just split it up right there. And then we get 2. I'm going to move the x squared. The square root of x squared is just x. I'm going to move it to the front. And then the root 2 I'll leave at the end. That's kind of the standard way we write it. We write the square root after it all, but either order is fine. And so that is simplified form. Go ahead and try out number 2. Now, I've shown you one way of reducing a radical. That can help if you're familiar with the different powers inside of a number, the different factors inside of a number. But if you don't know that, then what can help is a factor tree. And this helps especially for large numbers like I have here. So I have the cube root of 3780 and g to the 4th. So what I'm going to do is I'm going to take 3780 and I'm just going to look at what's the prime factorization of this thing. So I'm going to break it up. 3780 is the same thing as 378 times 10. 10, of course, is 2 times 5. And those are prime numbers, so I'm going to stop there with that part. Now 378, if you don't know how to break this up, or you don't know two numbers that multiply, just start with the smallest prime number and go from there. 2 is the smallest prime number, and 378 can be divided by 2. So 378 is the same thing as 2 times, let's see, let me make sure of that. Yes. 189. That's the same thing as 9 times, let's see, 21, I believe. And 9 is the same thing as 3 times 3. 21 is the same thing as 3 times 7. And so what I have here is I have prime numbers at the end. I've got 2, 3, 3, 3, 7, 2, and 5. Once you get prime numbers, there's nothing else you can do, right? Prime numbers are 2 is the same thing as 1 times 2. There's no reason to write down 1. Okay, now the goal here is to simplify the radical down. And the way we do that is we look for groups of however many whatever the power is. So we're looking for three numbers that are the same thing. In this case, it just so happens there are 3 3s in there. There's only 2 2s. If there was another 2, we could also take that out, but there's only 2 of them. There's only 1 5 and there's only 1 7. So what that means is that we can take out a single 3 from the outside. 3 3s is the same thing as saying there's 27, which is 3 cubed. 27 is inside of 3780. So in other words, I can rewrite 3780 as the cube root of 27 times, let's see, 3780 divided by 27 is 140. And 27 is the same thing as 3 cubed. I can break up the radical over that multiplication. And the cube root of 3 and 3 cubed cancel, so we get 3 times the cube root of 140. Okay, now we can talk about g to the fourth. And variables can also be broken down the same way. It's a little bit easier because there's not really much else there is to it. G to the fourth is the same thing as g squared times g squared. And those are the same thing as g times g, g times g. Again, we're looking for 3 of the exact same thing. There are 3 g's here. And there's 1 remaining. So what I can do is I can immediately factor this thing out. I don't have to go through this whole process, which I can do, obviously. I can go g cubed times g, which is then, let me do it like this. Cube root of g, I'm just splitting up the fraction. That, of course, gives me g times the cube root of g. And that's simplified form. But what I can do right here is I just say, well, this means that there's a g on the outside. This means there's a 3 on the outside. And that means there's going to be 3 and g on the outside. So we're going to get 3g. And what remains on the inside? Well, it's going to be everything that's left over. That's going to be the 2, the 5, the 7, and the g. 2 times 2 times 5 times 7 is 140. And there's a g on the inside, which of course is what I've shown here. So if that makes sense to you, go for that, try that out. It tends to work out, again, for larger numbers that you don't know how it breaks down. So try that out on number 3. Okay, so for radical expressions, terms that have radicals in them, they are only like terms if they have the same power and radicand. You have to have both of those things to be able to combine them into one term. So for instance, 5 root 2 and 3 root 8, they have the same power of the radical, the square root, right? But they do not have the same radicand. Root 2 and root 8 are not the same thing. But if we can reduce them down to be the same thing, because I've shown you before that when you reduce it, the radicand changes, the inside bit changes. If they can be reduced to the same thing, then they are like terms. Of course, the 5th root of 2 can never be like terms with these because it has a power of 5 instead of a power of 2. Okay, let's try it out. So we have the square root of 8. The square root of 8 is the same thing as the square root of 4 times the square root of 2. 4 times 2 is 8. And the square root of 4 is 2. So we have, let's do a 200 at the same time. I'll use a factor tree for this one, just to show you another instance of it. This is 20 times 10. 20 is 4 times 5. 4 is 2 times 2. 10 is 2 times 5. This is a square root, so there's a 2 there. In other words, we're looking for groups of 2 of the same number. We've got 2 2s, and we have 2 5s, with a single 2 remaining. So a 2, a 5 is going to go on the outside, and a 2 remains on the inside. So 5 root 2 is the same thing. That hasn't changed. Now 3 root 8 is going to be 3 times 2 root 2. That's what root 8 equals. The 5th root of 2 hasn't changed. And the square root of 200 is the same thing as, well, there was a 2 on the outside, a 5 on the outside, and a 2 remaining. Each pair, each group that you find goes on the outside is only a single occurrence, not 2 of them, a single one. That's because the square root takes away those other occurrences. 2 times 2 is 4. The square root of 4 is 2. That's why I use only a single 2 on the outside. The same thing is true. 5 times 5 is 25. The square root of 25 is 5. Okay? All right, well, this can simplify down to 5 root 2 plus 6 root 2 minus the 5th root of 2 minus 10 root 2. And now you can see we do in fact have 3 like terms. Even though they were not like terms in the beginning, after we reduced them, they did become like terms. 5 plus 6 minus 10, that's going to be 11 minus 10, so just root 2 minus the 5th root of 2. So after you simplify the expressions down, you can see if you got like terms. Again, they have to be the exact same power and the same radicand. All right, try this out on number 4. So radicals are actually the same thing as a fractional exponent. So if we have the pth root of b, this is the same exact thing as saying b to the 1 over p power. The radical power is in the denominator of an exponent. So if I were to have something like this, let's do the pth root of b to some power m. This is the same thing as b to the m over p. M is in the numerator because it's an exponent. P is in the denominator because it's a root. Now, it just so happens that this is the same thing as b to the pth root of b, and that whole thing to the power of m. So you can actually decide which form you want to use. It tends to be that taking the root first makes it easier because the root makes a number smaller, and then the power makes a number bigger, so it's easier to work with smaller numbers. But that really, context will dictate which way you want to use it. So just keep this in mind. That's what a radical really is. It's just the same thing as a power, which means all the rules of exponents apply to the radicals. Okay, let's actually look at this one. Let's rewrite this as a power on the whole thing. It's the 4th root, so it's going to be the 1/4 power. And what I can do is I can, let's see, what's the best way of doing this? I'm going to write 48 to the 1/4 power times x to the 7th to the 1/4 power times y to the 12th to the 1/4 power times z to the 19 to the 1/4 power. That's just using the product to power rule of the rules of exponents. And we can simplify these statements down. Now, in this case, it's not quite easy. This portion right here, this is actually quite easy in this way because a power to a power you multiply. So we get the same thing as, let's see, y to the 12th becomes y to the 12 over 4, which of course is just y cubed. So that one was nice and easy. The rest of them, it doesn't really help to have it as a power. It's actually more helpful to leave it as a radical, in my opinion. So for the first one, we can have the 4th root of 48. Well, 48 is the same thing as 16 times 3. And I like 16 because 16 is 2 to the 4th power. So I can rewrite that as 2 to the 4th power. And that means I can break up the radical and reduce that. Now, x to the 7th is the same thing. Let me just write it like this. And 7 can be rewritten as 4 times x cubed. Again, the 4th root of x to the 4th power cancels, so that gives us a simpler statement. Now, y cubed is still y cubed. That hasn't changed. And then the 4th root of z to the 19. In this case, we have the 4th root of, and I'm going to use z to the 16 times z to the 3. And you're going to see that the 4th root of z to the 16 is going to cancel nicely. So, splitting up the radicals. I just did that right there, so make sure you understand how I broke them up. I just split all the radicals up over the corresponding parts. And now you can see, well, we're going to have 2 times the 4th root of 3 x times the 4th root of x cubed y still. This is going to be the 4th root of z to the 16 is the same thing as, well, z to the 16 to the 4th root. It's the same thing as 16 over 4. So we get z to the 4. And we can write this all in one statement. 2xy z to the 4 times the 4th root of 3x cubed z cubed. Okay, so this process, it kind of depends on what you like to think of it as. Again, the radical can help thinking about it. The exponential or the fractional exponent can help when you think about it that way. Whichever way makes more sense, do that. Okay, let's look at another couple cases. For this first one, this one actually is better to work with the exponent. Again, the power on the radicand, or sorry, the radical is in the denominator, and the power, like a cubed, is going to be in the numerator. In this case, we have like bases and they're multiplying, so we can add the exponents. And here we have fractions that need to be added. So let's get common denominators. That's going to give us 5 over 4. And this is the same thing as the 4th root of 5 of a to the 5th power. This can be rewritten as a times the 4th root of a. That's because a to the 5th is the same thing as a to the 4th times a. Break up the radical, and you're going to see a to the 4th root of that cancels, and you get this statement. Okay. For this next one, I'm actually going to simplify what I can from the first term. 32 is the same thing as 2 to the 5th power. So we're going to get the 5th power, the 5th root of 2 to the 5th power times x cubed times the 3rd root of x squared. And I can break up the radical to give me 2 5th root of x cubed times the cube root of x squared. In this case, it's going to be better to think about these as powers. So it's going to be 3/5 x to the 2/3. Like bases multiplying, so we get 3/5 plus 2/3. You need to get common denominators. So multiply by 3 over 3, multiply by 5 over 5. That's going to give me 9 over 15 plus 10 over 15, or 19 over 15. This can be split up using the same properties, same things I showed you, as 2x times the 15th root of x to the 4. If you want to go ahead and try that out to see that. So either one of these, this statement, if they don't want these kind of improper fractions in the power, then you need to do it this way. That would be simplest form because it's reduced all the way. Go ahead and try this out on number 5. Okay. So a simple pendulum, if you don't know what a pendulum is, it's just a, think of it like a rigid rod, so like a stick or something like that with a mass on the end of it. It just swings back and forth like a grandfather's clock. That's what a simple pendulum does. It just swings back and forth. It's a very nice, simple case of harmonic motion in physics. And it's given by this formula. What it turns out to be is that the period that this thing swings, how fast it swings through it, is actually only a function or a formula of L. L is the length of the arm. G is just a constant. It's the constant of gravity. And of course, pi is pi. So the only thing that really can vary here is L, which is interesting that the length of the arm is what dictates how fast it goes through its period. But That's what you can find doing physics. So if we know that g equals this, 9.81 meters per second squared, what period does the pendulum have that is 4 meters long? So in other words, we have this simple pendulum. This length here is 4 meters. And we're asking, what's the period that it swings through? How fast is that period? It's like hanging onto the ceiling. That's what I'm drawing here. Well, to do that, all we have to do is plug it into the expression. The square root of L is now 4. That's all that's being said here. Is L is 4 meters. And gravity is 9.81. I can use a property of exponents. Split this radical up. And that's going to give me root 2 on top. And that, of course, multiplies the side thing, giving me 4 pi over the square root of 9.81. This is an exact answer, but we can actually solve this thing. If you plug it into a calculator, you're going to see it's going to give us just about 4 seconds. It's going to be in seconds because gravity is in meters per second squared. And so we have seconds as the unit of time. So a 4 meter long pendulum, as long as it's a simple pendulum, there's no other forces, nothing else acting on it. A 4 meter long pendulum is going to swing in 4 seconds. Okay. With this in mind, try out number 6.